So, hello everyone. Uh, Before continuing with functions and before learning anything else, this lecture is just going to be a review. It's just going to be a review of trigonometry that most of you might have learnt in high school. Actually, according to the course plan, I should have assumed that you must be knowing this, but still, I think that there's no harm in just revising all the concepts once again and probably reminding you of the trigonometry that you might have learned back in high school, and also probably giving a new idea or giving you a new perspective of trigonometry that probably you might not have seen in your high school. So trigonometry, as you might have learnt in your high school, has something to do with a triangle. Alright, it has something to do with a triangle, particularly a right angled triangle. Right, so a right angle triangle is a triangle where one of the angles is 90 degrees, and this degrees, you must have learnt, is a way to measure. That's the way we measure angles. It's how we quantify uh, the amount of rotation. So a quick background is what is a degree. Right, this is actually not needed, but still I would like to just you know explain it in brief what exactly a degree is, how it is defined. So if I take a circle, say this is a circle, obviously my drawing isn't perfect, but let's say this is a circle, and let's say this red line is such that it divides the circle into two equal parts. It appears that it's not equal, but just say that this exactly cuts the circle into two equal parts. Similarly, I can draw another red line, and now let's say I've divided the circle into four equal parts. Similarly, if I draw another one like this and another one like this, so now I have divided my circle into 8 equal parts. It's like a pizza, right? Each of this is like a slice of pizza. So a degree, how is it defined? So it says you take a circle, and like just like we sliced here this circle into 8 equal parts, say with the help of many such lines, if we chop this circle into 360 equal parts. So if we were to chop this circle into 360 equal parts, let me just zoom on one of those parts. So if I were to chop this circle into 360 equal parts, then the amount of rotation, so the amount by which I would have to rotate to, if am here, if I'm on this arm, so the amount that I have to rotate in order to reach this arm, this is termed as 1 degree. So what is a degree? So if I take a circle, chop it into 360 equal parts, then the amount of rotation equal to one such part is called as 1 degree. So what that means is, sorry, if I have a circle, then if I divide it into 360 equal parts, if I rotate by an amount equal to one part, it is called as 1 degree. If I rotate by an amount equal to two such parts, it is called as 2 degrees. And if I rotate the entire circle, then that is as if I've rotated around all the 360 parts, and hence we say that an entire circle, if you rotate around an entire circle, it is 360 degrees. Alright, now why a circle was divided into 360 degrees? Well, someone just decided that 360 is a good number. He could have also divided into 400, and today the definition of what we call as 1 degree might have been different. This is how the person who defined degree defined it. The reason why this 360 has come is that ancient people thought that 1 year is roughly 360 days, which is quite accurate considering that they knew this fact around thousands of years ago. So they thought that a year is 360 days. And what is basically a year? A year is a time period after which everything repeats, right? January, February, March, April, It's like we are going around a circle. So it's like we are going around a circle starting from January up till December, and again January starts and then the next December. So a year is like a circle, and after 365 days, all the months repeat itself. So they thought that a year has 360 days. That's why they divided the circle into 360 equal parts. So each part kind of representing one day of our life. That's just a background. I know this has become a bit too informative, but that's okay. Alright, now coming back to our main topic of triangles and trigonometry. So, you must have learnt two properties in high school. I just want you to recall those two properties. I will essentially tell you, and if you already don't know it, I will also explain those. So, the first one is that if you take any triangle, let's say I just name it A, B, and C. If I add all the angles in these triangles, if I add the values of all the angles in these triangles, angle A plus angle B plus angle C, it will add up to 180 degrees. I'm pretty sure you must have learned this. Alright, I'm not going to prove this. Those who are curious, they can check out for a proof online. But for now, we'll just say that this is a matter of truth. It's just true. It's true. For some reason it's true. That's how we are going to treat it. So the sum of angles of a triangle is 180 degrees. That's the first fact I would like you to recall. Remember this, I'm not going to repeat it. Alright, this I expect you to remember this from your high school knowledge. The next thing is, let me just draw a triangle A B C. Henceforth, the way I will represent a triangle is I will name each of the vertex by some letter like A, B, and C. Now, if you look at this angle A, if I look at this angle A, it is formed by this AB and AC. So these AB and AC are the ones that help in forming this angle A. So the side that is not involved in forming angle A, that is side BC, that we call as side opposite to angle A. So this is side opposite to angle A. So henceforth, this is how I am going to name a triangle. So how will I name it? I am going to draw any triangle as A, B, and C. The side opposite to angle A, I'll denote it by small a. The side opposite to angle B, I'll denote it by small b, and the side opposite to angle C, I'll denote it by small c. So is this clear? So if I draw any triangle, henceforth this is how I'm going to represent it. So this is angle A. Side opposite to angle A, I will denote it by the letter small a. Side opposite to angle B, I will denote it by the letter small b, and side opposite to angle C, I will denote it by the letter small c. This is how I'm going to represent triangles henceforth. Now so I have given you this fact. So let's make a deduction based on this fact. Suppose we have a triangle. Let's say a right angle triangle. A right angle triangle is where this angle is 90 degrees. And 90 degrees, if you see, it's like rotating 1/4 of a circle. It is 1/4 of rotating an entire circle. So it's 1/4 of 360, that is 90. So if I take a right angle triangle, and by the notation I have introduced just now, so let's say this is A, B, C. So this becomes small a, this becomes small b, and this becomes small c. Let us say that this angle, this is angle B, right? Instead of writing it as angle B, I'm going to give it by the Greek letter theta. I just don't want to write this angle sign each and every time. So I'm going to call it the Greek letter theta. So by this fact that we have discussed, angle A plus angle B plus angle C must be equal to 180 degrees. Angle A plus angle B plus angle C must be equal to 180 degrees. So what that means is that angle A plus angle B plus angle C is 180 degrees, but angle A is 90 degrees, and angle B, I'm calling it as theta, plus C must be 180 degrees. This means that angle C must be 90 minus theta degrees. So this angle right here is 90 minus theta. Okay, let me just take a blank part of this slide. So what I've drawn so far, so this was A, this was B, this was C, small a, small c, this is small b. So I said if this is theta, I have shown that this angle must be 90 minus theta. 90 minus theta. What that means is if this angle is 10 degrees, this is 90 minus 10, that is 80 degrees. If this angle is 20 degrees, this is 70 degrees. Alright. So henceforth I am going to represent a right angle triangle like this. So this is right, this symbol represents the 90 degree. If I say this is theta, from now on you must understand that automatically this is 90 minus theta. Alright. Another fact that I want you to recall from high school is that if I draw a triangle, let's say A, B, C, if I take this triangle, alright, so by our notation, this is small a, this is small b, and this is small c. And let's say if I measure these angles, if I find what are the values of these angles, suppose I find out that angle A, value of angle A is greater than angle C, and that is greater than angle B. Suppose I find out that this is how the values of the angles are in this triangle, then that means that the length of side opposite to angle A, that is length of side A, that must be greater than the length of side opposite to angle C, and that must be greater than the length of side opposite to angle B. So you must have learned this. So if in this triangle, if angle A is greater than angle C, then the length of the side opposite to angle A must be greater than the length of the side opposite to angle C. So you must have called, somebody must have stated this property in school as that uh, the side opposite to the greater angle is greater. Alright. Now let me just give you a brief logic why this works. Suppose you have an angle, let's say this is point A, this is angle A, alright, and I have not shown it here, but let's say if I extend this, this is actually forming a triangle, let's say. So this is the third side of the triangle that I am not showing right now. This is the third side of the triangle. This is small a, let's say. If you see, if you increase angle A, if you increase the value of angle A, you should see that the length of side A increases automatically. Let me just redraw this over here. What you must see is that if you take this angle A, alright, if you take this angle A, and if you were to increase this angle A, then the length of the side opposite to angle A also increases. Can you see this? So initially when angle A was this much, this is the length of the side opposite to angle A, whereas when you increase the angle, now this is the length of the side opposite to angle A. So you can visualize this as if this is a crocodile that has opened its jaws. So you can visualize as if this is a crocodile that is opening its jaws. So the wider the mouth of the crocodile is, so the wider the mouth of the crocodile is open, this distance will keep on increasing. If the crocodile opens its mouth even more. So by that logic, if you increase an angle, then the length of the side opposite to it increases. That's why this property makes sense. There is a proper proof for it. There is a rigorous mathematical proof for this. There is a proper mathematical proof for this, which I'm not going to get into. This is just a way I would like you to understand why in a triangle this property holds true. This is the reason why if you take an equilateral triangle, all of your sides are equal, therefore all of the angles as well are equal. What this property states, if angle A is greater than angle C, then side A must be greater than side C. But here, because all the sides are equal, A equals C equals B, angle A equals angle B equals angle C. Alright. Similarly, this is the reason why in what we call as an isosceles triangle, you must have done this, all of this in school. So in an isosceles triangle, if let's say these two sides are of the same length, say 1 centimeter and 1 centimeter, so because if these two sides are equal, so if side, let's say this C, this is B, so let's say side C and side B are equal, then the angle opposite to side C, that is angle C, and the angle opposite to side B, that is angle B, these two must be equal as well. Alright, these two must be equal as well. So this is another fact that I want you to remember. Now the most important thing that I want you to recall is the famous Pythagoras theorem. So if I have a right angle triangle, let me call it A, B, C. Alright, the side opposite to the right angle, this we give it a special name, we call it as hypotenuse. We call it as hypotenuse. You must have learned this in high school as well. We call this as hypotenuse. Alright. Now note that this angle is theta. If this angle is theta, this angle is 90 minus theta. I have discussed this at the beginning of this lecture. Alright, henceforth I am going to write it like this. Note that angle C plus angle B is 90 degrees, right? Because angle A is 90 degrees. What that means is theta, this is theta plus 90 minus theta is 90 degrees. So it is as if, say, if theta is 10 degrees, then 90 minus theta is 80 degrees. If theta is 20 degrees, 90 minus theta is 70 degrees. If say theta is just 1 degree, then this is 89 degrees. What you must note that even if theta is very small, let's say 0.5 degrees, this is 89.5 degrees, 90 minus theta. But this is always less than 90 degrees. Are you able to see this? So 90 minus theta plus theta is 90 degrees, right? Therefore, theta will always be less than 90 degrees. This is only for a right angle triangle. If angle A is 90 degrees, then 90 minus theta plus theta must be 90 degrees. So theta must be less than 90 degrees and 90 minus theta must be less than 90 degrees. What this means is that the largest angle in a right angle triangle is the right angle itself. So the 90 degree is the largest angle in a right angle triangle. And as we have already discussed, the side opposite to the greatest angle should be the greatest side. So by that logic, side opposite to the 90 degrees angle, which we have named as hypotenuse, hypotenuse is the largest side, hypotenuse is the largest side in a right angled triangle. So now what I want you to recall is the important Pythagoras theorem. So I'm pretty sure you must have learned this. What the Pythagoras theorem states is, according to this diagram, the value of hypotenuse square, alright? So if you measure the value of the hypotenuse and if you square it, that should be equal to the sum of the squares of lengths of other two sides, that is a square, the value a square should just be b square plus c square with respect to this diagram. Alright, this is the Pythagoras theorem. So a very classic example that you must have solved in your high school is, this is 90 degrees. Let's say this side is 3 centimeters, this is 4 centimeters. You must have been asked to find out what is the length of this side. You can pause the video if you would just like to try this out and verify the Pythagoras theorem. But if you might have done this a bunch of times in school, you must easily know that this side square is just 3 square, that's 9, plus 4 square, that's 16, which is 25, and thus the length of this side is 5. Alright, the length of this side is 5 by Pythagoras theorem. Observe that Pythagoras theorem obeys with our fact that the side opposite to 90 degrees is the largest side. So in this triangle, if you see, this is the largest side as we expect it to be. Hypotenuse must always be the largest side in a right angled triangle. Now let's come to the actual topic of interest. Now let's come to the actual topic of interest, that is trigonometry. If I'm not wrong, you must have learned trigonometry in high school as well. I'm sure you must have learnt trigonometry in the past in the high school as well. But again, here we are going to revise all that, and probably you might get a completely new perspective of trigonometry that you might not have had in your high school days. Note that this lecture is very important. This very basic lecture on trigonometry, it now might seem very trivial, that it now might seem as if you have already learnt all of this in your school days, but note that this is a really important lecture. Even though all of this what I've discussed so far seems very trivial, very basic, such a basic understanding is required so that you can grasp whatever we learn further, and that will help you to understand college mathematics more easily. So, in your school days, I'm pretty sure you must have described something, means you must have defined something as sine theta, cos theta. You must have at least heard these words, alright, in high school mathematics. Now, what I'm about to tell you is why exactly do we define these quantities. I'm going to tell you something that probably was not discussed in your high school days. Why we define these? Why we define these? Aren't we happy with the Pythagoras theorem and all such things? For which I want you to make a observation here along with me. I'm going to draw a right angle triangle, the one that we have already discussed earlier. A triangle having one side as 3 centimeters, one side as 4 centimeters, and as we solved earlier by Pythagoras theorem, this must be 5 centimeters. Now, don't worry about exactly from where I'm going to get the values. Right now, let us just say that I just drew such a triangle and I measured what the values of these angles are. So this is 90 degrees. I found out that this angle is actually 53 degrees. It's rough, it's not exactly 53 degrees, but approximately this is 53 degrees. And I found out that this angle is 37 degrees. Don't worry how I got these values. Right now, you can just think as if I actually drew a triangle somewhere else of 3 centimeter, 4 centimeter, 5 centimeter, and I actually measured what these angles are, and I found out that this is 37 degrees and this is 53 degrees. Now, see, this is the most important part now. I'm going to draw another triangle. Alright, I'm going to draw another right angle triangle. The base is going to be 6 centimeters. The height is going to be 8 centimeters this time. And by Pythagoras theorem, you can easily find out that this is 10 centimeters. Do you see some relation between these two triangles? You can pause the video to think about it. Are these just two random right angle triangles, or is there a relation between the two? Alright, so If you could figure it out, then very good, you are on the right track. If you observe, this 6, it's just double of 3. This 8 is just double of 4. And this 10 also is just double of 5. So what that means is this right angle triangle is just a magnified version of this right angle triangle. So it's just all of, if I stretch this right angle triangle, make this 3 centimeter double of what it is, if I stretch this 4 centimeters and make it double of what it is, automatically I should end up with this right angle triangle. It's like kind of, you can think that we are going in a 2x zoom, right? We are zooming it 2x. So this triangle, it's just as if you take an image of this triangle and you have just zoomed it up 2 times. So you get such a triangle. What is interesting here is that if I measure this angle and if I measure what is the value of this angle, it turns out that this angle somehow magically is again 53 degrees. And this angle is somehow again 37 degrees if I measure it out. In fact, there is nothing special about the 2x zoom. Alright, there is nothing special about the 2x zoom. If I were to draw a third triangle over here, and okay, suppose this becomes 9 centimeters right now. Suppose this becomes 12 centimeters. This, by Pythagoras theorem, this side square will be just 9 square 81 plus 144, and you can just solve this. This is just 225, so you can find out that this side is just 15 centimeters. So actually, if you see, it's just like a 3x zoom of this triangle over here. So it's like you multiply 4 by 3, you multiply this 3 by 3, you get this side 9 centimeters, and this hypotenuse 5 centimeters. If you multiply by 3, you get 15 centimeters. So it's just a 3x zoomed version of that triangle over there. What is special is that if I now find out, measure what is this angle, what is this, it just turns out that this is also again 53 degrees. This is also again 37 degrees. What this means is, let me take this triangle. Alright, let me take this triangle. This is 3, this is 4, this is 5. This angle is 53 degrees. So what is the length of side opposite to 53 degrees? It is 4 centimeters. In this triangle, length of side opposite to 53 degrees is 8 centimeters. In this triangle, length of side opposite to 53 degrees is 12 centimeters. There is nothing special about this. However, what is special is that if I were to find out what is the ratio, if I were to take the length opposite to 53 degrees in this triangle, that is 4 centimeter, and if I divide it by 5 centimeters, the hypotenuse, so if I take side opposite to 53 degrees and if I divide it by the hypotenuse, that is 4 by 5, which is nothing but 0.8. Alright, that is 4 by 5, nothing but 0.8. Now if I take the 2x zoomed triangle having sides as 6, 8 and 10 centimeter, this is 53 degrees. Now if you were to see what is the ratio of this side by this side, it is 8 by 10, it is again 0.8. Similarly in this triangle, the ratio of side opposite to angle 53 degrees divided by hypotenuse is 12 by 15, which is again 0.8. So what this means is, if you take any right angle triangle in this world having this angle as 53 degrees, so this automatically becomes 37 degrees, right? These two must add up to 90 degrees. If you take any such right angle triangle in this world, this length might keep on changing, this length might keep on changing, but the ratio of this length, this side divided by hypotenuse, is always the same. It's always 0.8. It's nothing special about the ratio of this side to this side. Even if you take the ratio of this side to this side, say in our example 3, 4, 5, that would be 3 by 5, that is 0.6. Similarly, in the 2x zoomed triangle, that will be 6. This is 6, 8, 10. So if I take the ratio of this side and this side, 6 by 10, which is 0.6. What that means is, if I draw any right angle triangle having 53 degrees and 37 degrees as the angles, ratio of any two sides always remains the same. This is the important fact. And it does make sense, right? Because if you take a 3, 4, 5 triangle, 3, 4, 5 triangle, the 2x, it's just a zoomed picture of it. It's just as if you zoom it. So even if you zoom it, all the sides are increasing by the same proportion. So the ratio of the any two sides is going to remain the same. And even if you zoom it, the angle, note that the angle, the amount of rotation won't change. No matter whether it is a 3, 4, 5 triangle or it is a 6, 8, 10 triangle, even if you zoom this 2 times, this angle is not changing. This angle is not changing even if you zoom it. Try to visualize this. Pause for a moment. Try to visualize as if you are zooming it. Alright. Try to visualize that this is initially like this, and note that even if you zoom it and make it so large, the lengths are going to change. The lengths are going to change, but the angle, the amount of rotation is not going to change. Alright. So this gives us an important fact. This is nothing special about 5337. If you take any right angle triangle, say this angle is theta, this angle is 90 minus theta, no matter how many such triangles you take. So let's say there's nothing special about 5337. If I take a 30 degree, 60 degree triangle, alright, and even if I take a bigger version, even if I take a bigger 30 degree, 60 degree triangle, the ratio of any two sides, say this side to this side, so the ratio of any two sides, or let's say if I take the ratio of this side to this side, actually it turns out that for 30, 60, 90 triangle, that's 0.5. No matter how big this 30, 60, 90 triangle is, the ratio, so the ratio of this side to this side in this smaller triangle and this bigger triangle is going to be exactly the same. That is why we define these ratios. Alright. So in a right angle triangle, if this is theta, if this is 90 minus theta, alright, wait, let's just name it A, B, C. So by our notation, this is small a, this is small c, this is small b. What that means is the ratio, even if I take a bigger version of this triangle, the ratio should remain the same. So these ratios, the ratio of sides, are actually important numbers that we make note of. So how does it help? So if I say know a triangle, let's say 30 degrees, this is 60 degrees. Alright. Suppose for this triangle I know that the ratio of this side to this side, so the ratio of side opposite to 30 degree to the hypotenuse is 0.5. So tomorrow, even if I have a bigger triangle, and if I just know the length of this, I know that even for the bigger triangle, the ratio of this side to this side should be 0.5. So this side should be double the length of this side. This is what motivates us to define all of these ratios. And you can define any ratios, right? You have three sides. You take ratio of any two sides, it's going to be the same. And it's nothing special that you should take, say, only b by a as the ratio. Even if you take a by b as a ratio, even that ratio should remain the same. So it doesn't matter. Alright, it doesn't matter. So we just give special names to them. So in this triangle, if this is angle theta, the ratio of side opposite to angle theta, to So if I take this theta, so the ratio of side opposite to angle theta divided by the hypotenuse, that is what we call as sine theta. So sine theta is just opposite side divided by hypotenuse. So in this diagram, that's just b divided by a. Then we just define something called as just a name. Sine and cos is just a name. I could have called it, instead of sine theta, I could have called this like Superman theta, and I could have defined Superman theta as side opposite to angle theta divided by the hypotenuse. It's just a way of calling it. There's okay, there is, it's just, there's nothing great about it. It's just a name, sine, cos. There's nothing intimidating about it. So cos theta, we will define it as side adjacent to angle B, so that is C. Note that there are now two sides adjacent to angle B. Even side C is adjacent to angle B. Side A is also adjacent to angle B. Whenever I say side adjacent to angle B or side adjacent to angle theta, that's going to be the side which is not the hypotenuse. So in this case, that is C. So side adjacent to angle theta divided by the hypotenuse, that is A. So we just define these quantities. So what does it mean? Because the ratio remains the same no matter how big the triangle is. If I take a 30-60 triangle, this is the ratio, right? Sine theta is a ratio. So doesn't matter what 30-60 triangle I take in this world, sine 30 is always going to have a fixed value. Cos 30 is always going to have some fixed value. Now who stops us? I mean, we can define any ratio, right? I could define even b by c is a ratio. Even b by c is a ratio. So let's just give it a name. I am giving it the name tan theta. Again, I could have written this as Batman theta. Nobody stops me from doing that. You could call this Spider-Man theta. I'm just, I mean, people have just named it as tan theta. There's nothing great as in such about tan theta. There are also explanations why this is named as tan, cos and sine, but it's just a name. That there's nothing great about the name. So I'm just going to call b by c, so side opposite to angle theta divided by side adjacent to angle theta, as tan theta. But note that this b by c is nothing but b by a. If I take b by a and if I divide that by c by a, I will get b by c, right? So this b by a by c by a, that is b by c, that is tan theta. However, b by a is sin theta and c by a we have defined as cos theta. From here you get your first trigonometry formula that you might have learnt in high school. Tan theta is sin theta divided by cos theta. This is how you get this formula. So there is actually no need to memorize these formulae. You can literally sit through, develop all this logic that I have mentioned here, and you can yourself derive all of these formulae. Not just this formula, all the trigonometric formulae, at least the basic ones that you must have learnt in school, can be derived in this way. Again, who stops us? I mean, why to define b by c? I can define c by b also as a ratio. Even that should remain constant no matter how big a triangle is. So I'm just going to give it the name cot theta. But note that c by b is just, it's just a reciprocal of b by c, right? It's just 1 divided by b by c. So 1 divided by b by c, that is c by b. But b by c we defined as tan theta. So your cot theta just becomes 1 divided by tan theta. Alright. Again, I've just derived this formula just by logical reasoning. There's nothing great about it. And if cot theta is 1 upon tan theta, cot theta is 1 divided by tan theta. But note that c by b is also c by a divided by b by a. So by that logic, it is also cos theta divided by sin theta. So this is also cot theta, which is 1 by tan theta. Right? This is how all your high school identities were derived. back then probably your teacher might not have told you the logic. They must have just told you to remember sine is opposite by hypotenuse, cos is adjacent by hypotenuse, then tan theta is sine theta by cos theta. But no, there's actually a logical reasoning. I can define more, right? I mean, who told that I should define only b by a? I could have defined a by b, right? So a by b, I just give it a special name. So the ratio of side, so the ratio of hypotenuse divided by opposite side, I'm going to call it as cosec theta. That's just a name I'm going to give it. Again, I could have called it anything. I could have called it Hulk theta. Nobody stops me. It's just a name. So I'm going to call it as cosec theta. I'm going to call it as cosec theta. And note that this a by b is just the reciprocal of b by a. So from here I get that cosec theta is 1 upon sine theta. It's just the reciprocal of sine theta. And already we can also define one more ratio. If I define b by a, c by a by b, I could have also defined a by c. I could also define a by c. So we are going to call this as sec theta. So what is sec theta? It is just the ratio of hypotenuse to a side adjacent to angle theta. Sec theta, and again the a by c is the reciprocal of c by a, and therefore sec theta is 1 by cos theta. So let's summarize whatever we have written here. Alright, so if I have a triangle, this angle is theta, this angle becomes 90 minus theta. Alright, this is say A, B, C, this is A, this is B, and this is C. So I defined sine theta as, what is sine theta? It's side opposite to angle theta divided by hypotenuse. So it's B by A. And what all we derived? Cos theta we call as C by A. It will take some time, but eventually with practice you will be able to write it very quickly. Tan theta, we just derived that this is nothing but sine theta divided by cos theta. Then we define something as cot theta, which in the diagram if you see, cot theta is a C by B. It is 1 upon tan theta, and it is nothing but cos theta divided by sine theta. Then the reciprocal of sine theta, it's cosec theta, it's 1 divided by sine theta. So in the diagram it's just A by B. And last sec theta, which is just 1 by cos theta, which in the diagram is just A by C. We can create, okay, now there's one more very interesting fact here. So this I found of theta, right? This I found of theta. I could also define all of these trigonometric ratios for this another angle, right? 90 minus theta. So let's write what is sine 90 minus theta. How did we define sine? It is the ratio of side opposite to angle divided by the hypotenuse. So what is side opposite to angle 90 minus theta? It is C in this diagram. And what is the hypotenuse? It is A. So C by A is sine of 90 minus theta based on how we have defined sine. However, see this is C by A, but C by A is also cos theta. This is how you get the other formula from high school, that sine of 90 minus theta is actually cos theta. There's nothing great, it's very logical. Because see, if you take angle theta, already if you take angle theta, side adjacent to angle theta, if you see by this diagram, the side that is adjacent to angle theta is actually the side that is opposite to angle 90 minus theta. So if you take the side ratio of side adjacent to theta and divide it by hypotenuse, or you take the side opposite to 90 minus theta and divide it by hypotenuse, it is the same thing. It is the same thing. And thus sine of 90 minus theta is cos theta. This is how you get the formula. It's not just a random math formula. This is the logical reasoning why this formula holds true. Similarly, if I write cos 90 minus theta, it is just side adjacent to 90 minus theta, angle 90 minus theta, that is B divided by hypotenuse A. But note that this B by A is just sine theta. So from this you get another formula, that cos 90 minus theta is sine theta. You can write one more formula by the way. If you see what is cot 90 minus theta. How did we define cot? Cot is the ratio of, if we go back, okay, let's just see here. Cot we have written as C by B. So what is it? So with respect to angle theta, it is the ratio of adjacent side to opposite side. So with respect to angle 90 minus theta, cot theta, cot theta is the ratio of side opposite to angle 90 minus, sorry, adjacent to angle 90 minus theta, that is B, to the side opposite. So it's adjacent by opposite. But note that this B by C, it is just what is, if I define what is tan theta was just opposite by adjacent, B by C. From this you get your another high school formula that cot 90 minus theta is tan theta. I hope you all are understanding what I'm trying to say. All of these identities can be logically derived. All of these identities can be logically derived. All of these identities can be logically derived. Alright, all of these can be logically derived. Let me summarize. What did I say? All the identities. Tan theta is sin theta by cos theta. Cot theta is cos theta by sin theta. It will take you some time to remember this very fluently, but no worries. It's 1 by tan theta. Sec theta is 1 by cos theta. Cosec theta is 1 by sin theta. It might be that I'm slightly rushing through this lecture, but that's because this is basics. So I'm just hoping that you all are able to easily understand what I'm trying to say. And then we have seen that sine of 90 minus theta is cos theta. Cos of 90 minus theta is sin theta. And cot 90 minus theta is tan theta. Similarly, tan 90 minus theta will be, you can prove for yourselves that it will be cot theta. You can also, so if this is true, 1 by cos theta should be equal to 1 by sin 90 minus theta. So that means sec theta should be cosec 90 minus theta. And similarly, cosec theta should be sec 90 minus theta. These, I mean, I don't think so. They must have introduced this in high school. You can write it. Probably these two and maybe even these three you might have seen in high school.